Hello, I'm Dr. Brian Fraser, and in this video I'm going to show how to use fork and exec together to spawn a new process and then have that second process, the child process, run a different application. So let's just get into this. I've written a program here called BOGO sort, which uses a particularly bad sorting algorithm to sort some data. So I'll just run it here. First build this. So I can run it by typing /BOGO sort, and then I can give it some space separated values. So 1, 2, 3, just give it a whole bunch here. So there's a small set, and we can see it comes back in sorted order. Now BOGO sort is really bad, so if I start to add more and more elements, it's going to take a bit longer. So it's now taking n factorial time actually to compute on average, the sorted set. So you can see I just added one more element and we're taking kind of 12 times as long as the previous set. And by the time we get up to 20 elements, don't bother looking. This video is going to be hours and hours and hours long. So that's the program I'm going to run. And what I want to do is I want to have one parent process that simply forks and execs this code here. So it just launches an instance of BOGO sort. We'll then try and make the parent process launch numerous instances of BOGO sort all at once. Okay, so let's start off with this. So there's a number of other videos that I put up on fork and exec describing each of fork and exec in detail. So I won't be covering those details here. Please have a look at those videos, which I'll link below in the comments. So the first thing we're going to want to do here is we're going to want to fork our current process. So I need to catch it in the PID. So PID type, let's call it PID equals fork. So that'll create two processes. Fork's going to return twice effectively, once in each process. So I can check if the PID is less than 0, well, it failed. So let's print out an error message. So P error, fork failed. Fork failed. And exit 1. Okay. So else, I don't really need an else here, but let's put it in just to make my logic a bit clearer. If the PID is equal to 0, we know we're the child. Child now execs. And then down here, we are the parent. So if you recall from the fork video, fork is going to return a negative number for an error, 0 if you are the parent, and 0 if you are the child, and non-zero, i.e. positive value, if you're the parent. So in here, we're now going to want to actually exec to replace us with the executable we wish to run. So we're going to run exec. Now there's a family of execs that we can call. I'm going to use exec v. See the exec video for a discussion of what we could do here. And I need to pass it two arguments. Hit control space. It'll tell us we need to pass in the file name, and then a char star const array, which is to say an array of strings. It's const, meaning we're not going to change it, so we can ignore that. So I'm going to pass it in an array of strings, and let's build that first. So I'm going to want to say here a character array. Let's call it args. Sounds good. And it's an array of strings. So a string is a char star in C, and then I can set this up in here as just a comma separated list of arguments. Now, by convention, the first argument to an application this is the command line arguments we're talking about, is going to be the name of the process I'm running. So it's going to be /BOGO sort. It's the name of my executable. And then I can pass in a comma separated list, continue my array with a bunch of other values. And if I just run BOGO sort on its own, we can see it gives me a little bit of help. It's looking for space separated values to sort. So the space separated is basically going to be the different arguments that get pushed together by the OS. So let's pass in some numbers. So I can pass in 1, 2, and 3. Let's keep it really simple to start with. Now as it turns out, this is a terrible set to choose, but it's good enough. And finally, this set of arguments must be null terminated. That's how Linux knows that we've hit the end of the arguments, because otherwise we just have an array. We'd have to tell it how big the array is. That gets a little awkward. So I now need to figure out what is the name of the executable. So I pass in the file name and then the args. Now, a trick here is the file name I could put in /BOGO sort, but I already did that above. So I'm just going to make this a bit shorter and put in args sub 0. So arg sub 0 is the first element of the array. The first element of the array here is the path that I'm executing. So that just simplifies my life that way. And then inside of the parent, I could do anything I like. So I'll put here do clever processing here. So we can do anything we like. We're going to have two separate processes, each with their own address space running. So let's just prove this will work. I've got a makefile here, a fairly simple makefile that I'm able to specify a list of targets, and I want to build BogoSort, which is in the current folder. At the end of this presentation, I'll walk through BogoSort just for those who are interested in what this .c file does for me. And then I'm also going to build my fork exec, fork_exec, which is my fork_exec.c function or file, in the same folder. And then the makefile is just going to use these arguments. I'm using all for turning on all warnings, so I get great help from the compiler. G for including debug information. I like to put in the stdc99 so I can use for loops in powerful ways. And then finally error because I want to turn all warnings into errors. And then the rest of the makefile simply builds my executable. So coming back here, I'm going to hit Control B, and it's not going to work. We can check out why. Scrolling all the way up, here we have unknown type PID_T. So I could Google that to figure out what's going on. I can look here and it's saying, well, it's in this line of the code. I can try man PID_T. It doesn't give me anything. So I'm going to try man fork. Give me some information on that. Now it comes back with GNU AWK extension. That's not what I want. So I'm going to do man2 fork for the programming reference. And here it suggests that I probably want to hash include uni_std. So let's do that here at the top. Hash include uni_std.h. std.h. Rebuild. Unknown name type here. So I could check through this a bit further. Turns out I need to bring in the type def. So I'm going to do hash include. And this is going to be pthread. pthread.h. And now it brings in the appropriate value there. It tells me here, next one, implicit declaration of exit. Exit is in standard lib, so hash include stdlib.h. And there we have it. Okay, so now we're compiling. Let's run it. So quit that. Here we can see my executable. I've got BogoSort there, which we were running before, and I can run fork exec. So I run fork exec, and it looks a little weird. It looks like it's taking forever, but in fact it took very, very little time. I'll hit enter here and we're back at the command prompt. Let me run that again just to watch what happens. So it looks like we never get the command prompt, but the command prompt is actually sitting here. The issue is that we have we forked, we did something in the child, but my parent never waited for that child to complete. So down here, I'm going to say parent wait for child, and we can just say wait. We're passing in null. It's a simple way. Why is that? Oh, I know why. We can do here man to wait, and it tells me that this is going to be in sys/wait.h. So we have to include the correct things here. So hash include sys/wait.h. And in fact here I think I can probably, let's try it, get rid of my hash include pthreads, and I'm going to switch here to sys types, because I'm not really using the pthreads here. Oops. And paste in what I highlighted there. So sys types. Let's see if that builds it. Yeah, we're building fine now. Okay, so let's rerun my executable. I can do, that was called fork exec, and we see here it actually goes through and executes. Just as if I had typed in ./BogoSort and then passed in the arguments here, I get the same sort of output. Of course, the PID at the front is changing because my program ID, I've got other processes that are launching in the background, other threads and so forth. Okay, so that gives us the basics here. Now let's make it so that Bogosort actually begins to take some real useful time here. So I'm going to pass in a few more arguments. I'm going to pass them in sorted order here. Turns out Bogosort is in general not smart enough to do anything about this and to realize that they're in nearly sorted order. It doesn't really help Bogosort. It just is a random sorting. And what I'm trying to do is I'm using this to take up time. So it's just you can imagine this simulating a sub-process that has some meaningful work to do. Now one thing is that my sort algorithm checks, is it already sorted? So I'm just going to make this slightly unsorted. So I reverse the first two elements, recompile. Now it's going to sort an array of 10 items. So /fork exec. And we can see it takes a little bit of time. If I ran this a number of times, sometimes it's going to come back very, very fast. It is a random algorithm. Other times it'll take quite a long time. So it takes 10 factorial, or big O of 10 factorial is the runtime here, which means it can be very, very slow. Now, I found through some previous experimentation that on my computer, running with 11 elements gives me a bit of time, but not, let's actually make that. Takes a bit of time, but not so much that I need to write another video later. So let's now see what we can do with this. We've got the actual child process being spawned here with my fork, and then this code is executed by the two processes. So both processes check if the PID is less than 0. Of course, it won't be if it succeeded. And we'd only then have one person checking, but if it was less than 0, then both of them check to see if it failed. We then check, are we the child? The child then quickly replaces itself, and then the parent can do something else. So let's print out, for example, here, printf parent is now doing something amazing. So this could be your program that watches a thread, or pardon me, watches a socket, accesses a database, computes something interesting, or even just waits on the sub-processes. That's perfectly fine to do. And then I'm going to printf here, parent is waiting on child process. Okay, so let me rebuild this, rerun that. So, parent's doing something amazing. This is while the child was executing. The child just happens not to print out anything at the start, but we could have it sort of, interspersed output here on the screen. It can get a little confusing. Okay, so that's the basics here on fork and exec, and then doing, something perhaps interesting in the middle, of which we're not really coding. Now, what if we wanted to launch multiple processes? We talked in the fork video how fork sets up two separate processes. We talked in the exec video about how when you exec, you basically wipe out everything in the memory space. Anything that was previously there is gone, which is why I'm passing in command line arguments rather than sort of storing something like an array that the function that gets exec simply accesses directly. I don't have like a global variable for this because it's blowing away the address space. Okay, so let's make it so that we can launch numerous processes. So first I'm going to create a define here at the top, num children. And let's start off with 2, just to keep it simple, and we'll later just bump that up. REN. So what I want to do is I'm going to run this in a loop, number of times, spawning the child processes, and then down here I'm going to run wait in a loop as well, because if I spawn 5 children, I need to wait for 5 children to all finish before I actually exit my program. If I don't do this, it leaves zombie processes. See the fork video for information on that. So, for int I equals 0, I less than num children, I plus plus. Again, I can do this because I'm using the C99 compiler flag for standard C. So I'm just going to run this through a number of times. That'll launch all of my children processes, and then down here at the very bottom, I can wait for all of them. And that will simply go through spawning them and then waiting for them. I'm not waiting for any particular one to finish, I'm just saying, well, I'm waiting for everything. Any of my child processes that finish. Now interestingly here, I am passing in the same command line arguments. And it's going to run differently in each of them. Let's see what happens. So we should see, if all goes well, each of the child processes finish at different times, and they'll each print to the screen when they do finish. I can actually bring in here, I've got the system monitor and Linux up and running. So we can see my CPU usage. There's the first one finished, so it ended the PID of 66 at the end. And the second one, we can't really see it here, but we can see that it was at 100% utilization on the CPU, and now it's finished it well. The PIDs were sequential because they were spawned back to back. But the solutions took quite a bit of time because I'm randomizing based on the PID of the process. So I could try that again. Let's just run that one more time and watch the processor utilization. We can see here that CPU 1 went up to 100% per second, but now the job has been moved to CPU 2 and CPU 4. Over time, we'll see that that switches. Linux has some sort of processor load balancing routines that may cause it to switch from one to the next. So we can see here that now one of the processes finished and the other one finished as well. They're both falling off here in the graph. So what's interesting is that if we wrote one process that tried to run BOGO sort twice sequentially, it would take effectively twice as much time as going on here, because we've got a quad-core computer. We can see all 4 cores here that Linux has access to, and we could then run 4 different children processes in parallel. So let's try that. I'm going to run this to 4, rebuild, bring that up, and let's just clear some space for us. Run fork. So we can see all 4 of them start up at once. And as they randomly finish, one finished, the second one finished, we'll see them falling off here, the third one, and then the last process, 100%, and it's falling off here. So we've seen that all of them were at nearly 100% utilization as we ran. So this would explain why we would want to use a process, is we get 4 times the computational power. Now in this case, of course, I'm squandering it on BOGO sort, but you could be doing something very interesting with that extra power that you couldn't otherwise do if you were executing on a single core. Okay, so that concludes what I wanted to say about fork and exec. We saw the example here on actually doing the fork, and then exec will wipe us out, clear the memory space. If I put in a command here, for example, printf, never going to see this. Doesn't matter what I put here because this is never going to execute. This command, the memory space has been replaced by the time we hit the exec command. Now, one last thing to mention is if you're running fork and exec as a pair, fork spawns a new process, exec replaces the current one with a different process or a different executable from the disk. One thing that can be challenging is this fork call can be expensive if you don't do it the right way. So Linux implements it very efficiently, and that a fork function call will duplicate the process. It duplicates only very small bits of data structures in the kernel. It doesn't actually go through and copy the entire process address space, because in a lot of cases a fork is very quickly followed by an exec. So here I'm simply creating a new array on the stack, which should be okay. I'm only changing the stack, and then we call exec to actually do the work for us. If instead I did some other work here, like if I had a global variable int g, and then down in here if I went and changed g, all of a sudden this change to the global variable means that the previous address space, the previous heap, or not the heap, pardon me, but the previous static store that the global variable was in is now all of a sudden changed. And Linux would therefore have to replicate that entire segment of memory. If I accessed, a linked list or something like that and changed some values in the linked list, I could potentially have to replicate a lot of data, clone a lot of different areas in the address space, and that might take Linux a lot of extra time. So the hint on this is between fork and exec, so between fork and exec, I want to do pretty much as little as possible. I want to not change global data. I want to not change any of the allocated data, memory allocated data, and so forth. Otherwise, it causes a lot of extra work to be done when Linux executes the fork before it does the exec. Okay, that's all I wanted to show. Thank you very much for watching.